All right, so to fully understand the net torque equation, we need to now look at another piece of it. So the first thing we need to talk about is the difference between net force and net torque. So just because there might be a net force of zero does not mean that there's going to be a net torque of zero. So for example, if I have two forces, one pushing up and one pushing down on a tiny little dot, I will have a net force of zero because I have the same amount going up and down. And in terms of torque, it'll also be zero. But that's not the case if I have something that's three-dimensional, like a ruler or a beam or something like that, where if I have a force pushing down on one side and pushing up on the other, I can have a net force of zero, but the net torque is not going to be zero because these forces will cause it to rotate. And looking at it, you look at it and go, oh yeah, that makes perfect sense. It's going to rotate if you push on it like that. And so therefore the net torque is not zero. So remembering our net torque equation, we need to first think about torque itself, which is force times distance, where it's either force times distance that's perpendicular, or the perpendicular force times the distance. And that is going to go into our net torque equation. So I'm going to just pause for a moment and I'm going to have us remember the net force equation. So when we had net force, then we had like our normal force or gravitational force, things like that, that would go in this blank. And then that was equal to mass times acceleration. Well, that is very similar to our net torque equation, but now we're going to have the sum of our torques are equal to, maybe it's the weight of the beam, and then there's a cable pulling up, and there's a person pushing down, something like that, whatever things are causing it to rotate. And that'll be equal to your moment of inertia times your angular acceleration. So thinking about how that's similar, this is net torque, this is net force. I like to think of net torque as the force that causes it to rotate, or my twisty force. And force is just a push or pull. So when I talk about torques, it's like how much it's being twisted. And then whatever goes in the blank goes in the blank for both of these. In the case of the torque equation, it's torques. In the case of the force equation, it's forces. Then there's moment of inertia. And in the force equation, it was mass. So thinking about if you're pushing on something, if it has more mass, it's going to have a smaller acceleration, or it's going to be harder to push. For moment of inertia, it's kind of like the same thing, but rotationally, because it's not just about the mass of something for moment of inertia, it's also about where the mass is. So trying to get something to move, and it could be really heavy or light, but it also matters the shape of it and how far away the mass is that you're trying to move and rotate. And then for torque, it's your angular acceleration, which is the rotational version of translational acceleration. So these are really the same equation. The difference is that the net force equation is translational and your torque equation is rotational. So now we're going to talk about the steps that are considered when we're doing these. So when you're doing one of these problems that involves torque, you're going to need to do a net torque equation. So you need to remember that net torque is equal to your moment of inertia times your angular acceleration. And you're going to start by solving the problem by drawing a free body diagram. So a free body diagram is the one where it actually has shape. You can't just put everything on a dot. And then you're going to make a net force equation for each direction. So the sum of the forces in the x direction and the sum of the forces in the y direction, and have that equal to ma. And then you're also going to do net torque equations. And for that, you only have one. There's no x or y direction. There's just one. It takes everything into account in just one. And that'll be equal to your moment of inertia times angular acceleration. Then you're going to look at these three equations, the sum of the forces in the x and y and your torque, and you're going to use that to solve for whatever it is that you're looking for. But conceptually, we need to think about what is a moment of inertia. So the first thing I want you to do is know that the equation for moment of inertia is mass times your radius squared. And this is what you really need to know, is just this equation here. But if you're in calculus, this is going to be the actual equation. So if we had like a dot and it was going around in a circle, then the radius to the middle would be this radius, and the mass would be the mass of the ball. And that would be for a point. But sometimes we have more complicated shapes, and I'm going to teach you about that. And then that's when this equation is going to be what you're technically using, but you don't ever have to use it, because all of the normal shapes, you'll just get the moment of inertia equation for them. And I'll show you what those are. So I want you to feel what a moment of inertia feels like. So start by rolling a pen in your hand and feel how easy it is to make it roll. So you're trying to initiate an angular acceleration of rolling, and that should be pretty easy. And then I want you to twist the pen this way around the middle. And you'll notice that it takes a torque to cause it to rotate or to cause it to stop rotating. So you need to apply a force in a specific direction to try to do like a twisty force, which is torque. And then I want you to do it this way and feel what that feels like. And out of these three, my guess is that the first one was the easiest. The second one was the second easiest, and the third was the third easiest. You'll notice that if you have the same angular accelerations, that first one is going to be the easiest to do. All right, so now I want to start trying to practice calculating the moment of inertia. So here I have a ball going around. Let's pretend like we're trying to make a solar system model, and this is a little Earth. And the radius is 1.2 meters, and it has a 3 kilogram ball. And so to calculate this, I just need to use the equation I equals mr squared. So here's the equation. I'm going to plug in my mass and my radius, and remember to square it. Plug that into a calculator, and I get 4.32. And that's all there is to finding the moment of inertia. That's it. That's all. The harder it gets. But what are the units? So just look at the original equation and plug in the units. So mass is in kilograms, radius is in meters squared, and that's all. So then you end up with kilograms times meters squared. If you have two of these balls that are rotating around, then I'm going to have two 3 kilogram balls, which means that my total mass is going to be 6 kilograms. So 3 plus 3 is 6. I have the same radius of 1.2. I throw that into a calculator and I get 8.64. But what if I wanted to do it with this ball and this ball separately? Well, for that, what I would do is my total moment of inertia is equal to the moment of inertia of the first ball plus the second ball. And so I use mr squared for both of them. I plug in the numbers. I get 4.32 for each of them, which gives me a total of 8.64. And you'll notice that that's the same moment of inertia as the other problem that we just did, which is good because it's exactly the same setup. So I would hope I get the same answer. All right. For moment of inertia of a wheel, it's the same exact thing, but now instead of two balls, you have hundreds of balls that are all in a circle, all at a distance of r away. And therefore, the moment of inertia of a wheel or a hoop, this is called a hoop, is just mr squared. So super easy. But what if they're different distances? Well, if they're different distances, then I have to do the method of one moment of inertia plus the other. And so to do that, I just need to use the equation of mr squared for each with the different radiuses. So they have the same mass, but different radii. plug it in, and I get 5.79. So here's an example of a playground toy. Each has 4 seats, or this thing has 4 seats, each of 5 kilograms, attached to very light 1.5 meter long rods. What that means is you do not need to worry about the mass of these rods. We're just going to ignore them. And then there's 2 kids, one that has a mass of 15 kilograms and one that has a mass of 20 kilograms, and they're going to sit opposite one another. So to find the total moment of inertia of this system, what I need to do is I need to notice that there are 4 seats. So I'm going to have 4 chairs here, plus the moment of inertia of the first child, plus the moment of inertia of the second child. So I'm going to do mr squared for each. And there's 4 chairs, so I did 4 times my moment of inertia for each individual chair. Plug in the numbers. Do some algebra. And I get 123.75. All right, so now that we have learned about finding the moment of inertia of something with multiple parts, we need to look at what it means if we make something into a ton of tiny pieces. So this goes back to the idea of using calculus to find the moment of inertia of a complex shape. So we did this one, it was just mr squared, and we added 2 balls together, and then we did a whole bunch of balls, and then we did 2 different rings, or we had 2 different distances of balls. And if I keep this up and then I have a hoop of those balls and then I make a hoop of another one and another one, what's going to end up happening is I will take the integral of all of these balls, in other words, find the moment of inertia of each one of these tiny balls and add them together, and I will get 1/2 mr squared. Or if you're in calculus, you can calculate it yourself. Or if you don't care, you just look at this up in your textbook and go, oh, look, this shape is 1/2 mr squared. But the reason why it's 1/2 instead of just mr squared is you'll notice that a lot of this mass is close to the center of the circle. It's not all at a radius of r. And so that's where this 1/2 comes from. In your textbook, you have a table of all of these things. The only one that you need to memorize is the cylinder or disc, which is 1/2 mr squared, which is the one we just talked about. And then the cylindrical hoop, or if, and this would also be for if you have just like a ball going around in a circle. That would also be mr squared. And then these are the only 2 that you should memorize. The rest of these will be given to you in the problem if you need it. Or you should be able to qualitatively tell me which one has a bigger moment of inertia. So for example, between these 2, this is like a solid ball. So like think a marble. And this would be where all the mass is on the outside. Think like a ping pong ball with air in the middle. And I know that this one will have a bigger moment of inertia than that one because all the mass is at a radius of r for this one. And this one, some of the mass is in the middle, some of the mass is here, some of the mass is close to the outside, and some of the mass is on the very outside. And so I know that this one has to have a bigger moment of inertia than that one because all the mass is all the way far away. And in fact, it does. This one is 2/5 mr squared, and this is 2/3 mr squared. This one is like the pencil that you were holding in the middle and rotating back and forth. This is when you held your pen by the end and kind of flung it around. This would be like if you took a piece of paper and turned it over and you rotated it around the middle of the paper. This one is like you take a piece of binder paper in a binder where this side is attached, or like a book, and you turn the page. So that's what all of these shapes are. So again, this is on page 232 in your textbook. So we will do more examples of these. Just check my other videos to see those examples.